Hello friends, welcome to our third class on magnetic circuits. A magnetic circuit is defined as the closed path traced by the magnetic lines of force. See here, in this core, a coil is wound on one of the limbs which is having n number of turns, and we are passing a current through that coil. Then, due to magnetomotive force developed by the coil, it creates magnetic flux or magnetic lines of force which passes through the core. We know that in an electric circuits there will be voltage or current sources and components like resistors, capacitors, inductors, etc., which may be connected in series, parallel, or a combination of both as per the requirement of the circuits. Similarly, in magnetic circuits also there will be magnetic materials having different reluctances which are connected in series, parallel, or a combination of both as per the requirement. Types of magnetic circuits. There are mainly two types of magnetic circuits. One is series magnetic circuit, in which, like the case of electric circuits, magnetic materials are connected in series and same flux passes throughout the core. The second type is parallel magnetic circuit, in which there will be more than one or two parallel paths. This is also like the case of a parallel electric circuit. See here, flux phi1 is coming and it divides it into two. The flux phi2 and phi3 depends upon the reluctance of the paths. Series magnetic circuit can further be classified into two. One is a simple series magnetic circuit where throughout the material the same core is there. The reluctance of the core is the same, the dimensions also will be the same. Another type is composite series magnetic circuit, in which the seriously connected magnetic materials will be of having different reluctances, μr1, μr2, μr3, μ0, different area of cross section, different length, etc. In this class, we will study about series magnetic circuits. Before going into studying that detailed explanations and problems, it will be better to note the formulas we have studied about magnetic circuits in a piece of paper and keep it aside, so that it will be helpful for reference. Now we will analyze a simple series magnetic circuit. A simple series magnetic circuit consists of a single core with a coil wound on the core which is having number of turns n. When we are passing a current I through this coil, a field is formed around the conductor, and the field formed around every conductor forms magnetic flux and it passes through the core. That magnetic flux is denoted by the letter phi and its unit is Weber. Now we will see how to calculate the magnetomotive force MMF, calculation of MMF. There are two methods. Method 1, reluctance method. We know that reluctance S is equal to L by mu0 mu r into A. That is, reluctance is directly proportional to length and inversely proportional to area of cross section. In an electric circuit, by Ohm's law, resistance is equal to EMF divided by current. Similarly, in magnetic circuit, reluctance S is equal to MMF F divided by flux phi. We know that F is equal to N into I, that is number of turns into current divided by flux. That is, MMF F is equal to this N into I, that becomes S into phi when this phi is brought to this side. N into I is equal to S into phi. Next method is BH method. We know that flux density B is equal to total flux divided by area of cross section. Also, B is equal to mu into H. Therefore, H is equal to B divided by mu when mu is brought to LHS. That is equal to B by mu0 mu r, since mu is equal to mu0 mu r. As said earlier, MMF F is equal to N into I, and the magnetic field intensity H is equal to MMF divided by length, that is F divided by L. But F is equal to N into I divided by L. When this L is brought to this side, H into L is equal to N into I, or N into I is equal to H into L. That is, magnetomotive force F is equal to N into I, which is equal to H into L. That is, magnetomotive force N into I is equal to H into L. Composite series magnetic circuit. In a composite series magnetic circuit, we can see that magnetic cores having different permeability, different area of cross section and different lengths are connected in series. See, let area of cross section of this section is A1, this section is A2, this section is A3 and that of that vacuum or air gap is AG. Similarly, length is for this core length is L1, for this core length is L2, for this one L3 and air gap is LG. The permeability of this core is mu R1, this one is mu R2, this one is mu R3 and that of air gap is mu 0. When a coil is wound which is having a number of turns N and we are passing a current I through the coil, a magnetic flux is developed which passes through the core. As these cores are connected in series, like the case of series electric circuit, the flux passing through the entire core will be the same. Now we will see how this composite series magnetic circuit is analogous to an electric circuit. We know that in this series connected electric circuit, total resistance or R equivalent of the circuit is the sum of these series connected resistances, that is Req is equal to R1 plus R2 plus R3 plus Rg. Similarly, in the case of this magnetic circuit which is connected in series, equivalent reluctance Seq is equal to S1, that is reluctance of this portion, plus S2, reluctance of this portion, plus S3, which is the reluctance of this portion, and Sg, which is reluctance of air gap. In electric circuit, R is equal to L by mho into A. Similarly, in magnetic circuit, reluctance S is equal to L by mu into A. That is, mu is permeability. But we know that mu is equal to mu 0 into mu R. Therefore, S becomes L by mu 0 mu R into A. As S is equal to L by mu 0 mu R into A, S1, reluctance of this path is length of this path L1 divided by mu 0 mu R into area of that portion A1. Similarly, reluctance of this portion is L2 divided by mu 0 mu R2 A2 and S3 is L3 divided by mu 0 mu R3 into A3 and Sg is equal to length of air gap Lg divided by mu 0 into Ag, area of cross section of that free space. Here mu r is 1 since relative permeability of free space is 1. Mu 0 of free space is 4 pi into 10 raised to minus 7. Therefore, the total reluctance S equivalent is equal to reluctance of this path plus this path plus this path plus this path, that is L1 by mu 0 mu R1 A1 plus L2 by mu 0 mu R2 A2 plus L3 by mu 0 mu R3 A3 plus Lg divided by mu 0 Ag. Next we will see how to calculate the magnetomotive force MMF of that circuit. There are two methods. Method 1 is by reluctance method. In electric circuit, current flowing through all the resistance is same, but voltage drop varies as per the resistance value. That is, total EMF E is equal to voltage drop here E1 plus E2 plus E3 plus Eg. But we know that E is equal to I into R. I is the same. Therefore, E1 is equal to I into R1. E2, voltage drop across R2 is equal to I into R2. E3 is equal to I into R3 and Eg is equal to I into Rg. Similarly, in this magnetic circuit, flux passing throughout the circuit is same, but MMF varies as per the reluctance of that particular path. That is, total MMF F is equal to F1, MMF of this path plus F2, MMF of this path plus F3 plus Fg. We know that MMF F is equal to I into N, that is equal to phi into S. Therefore, F1, that is MMF of this portion, is phi into S1, that is reluctance of this path, and MMF of the second portion is F2 is equal to 5 into S2, F3 is equal to 5 into S3 and Fg is equal to 5 into Sg. Therefore, total MMF F is the sum of all these MMFs, that is equal to F is equal to I into N, that is 5 into S1 plus 5 into S2 plus 5 into S3 plus 5 into Sg. That is 5 is common factor here. F is equal to 5 into S1 plus S2 plus S3 plus Sg, that is flux passing into reluctance of separate materials. Another method for calculation of MMF is BH method. See here, total MMF F is equal to MMF of individual magnets, that is F1 plus F2 plus F3 plus Fg. Let this is equation number 1. Magnetic field strength or magnetizing force H is equal to MMF F divided by L, or MMF F is equal to HL when we are bringing this L to this side. Substituting F is equal to HL in equation number 1, total MMF F is equal to I into N, that is F1, that is H1 into L1 plus S2 into L2 plus S3 into L3 plus Hg into Lg. But we know that H is equal to B by mu 0 into mu r. Therefore, this equation can be written as F is equal to H1, that is B1 by mu 0 mu r1 into L1, and this is B2 by mu 0 mu r2 into L2 plus B3 by mu 0 mu r3 into L3 plus Bg by mu 0 into Lg, since mu r is equal to 1 for air or vacuum. Now we will try to solve some examples of series magnetic circuits. In this example, a ring of diameter 21 centimeter which is having area of cross section 10 centimeter square is given. This ring is made up of two sections. One is a cast iron having relative permeability 166 and the other cast steel having relative permeability 800. There is an air gap of 0.2 mm between the joints of cast iron and cast steel. We have to find the ampere turns required to produce a flux of 8 into 10 raised to minus 4 Weber. That is, phi is equal to 8 into 10 raised to minus 4 Weber, and the area of cross section A is equal to 10 centimeter square. That is equal to 10 into 10 raised to minus 4, that is 10 raised to minus 3 meter square. As flux and area of cross section are given, we can find flux density. Therefore, flux density B is equal to phi divided by A, that is equal to 8 into 10 raised to minus 4 divided by this area of cross section 10 raised to minus 3, which is equal to 0.8 Weber per meter square. Also we know that B is equal to mu H. Therefore, H is equal to B by mu, that is equal to B by mu 0 mu r, since mu is equal to mu 0 into mu r. So, for air gap, H is equal to B by mu 0 because mu r is 1 for air or vacuum. This is equal to B 0.8 divided by mu 0, that is permeability of air. We know that 4 pi into 10 raised to minus 7. This gives 6.366 into 10 raised to 5 ampere turns per meter. Here the air gap is 0.2 and here it is 0.2. So total air gap becomes the sum of these two. That is, total air gap L is equal to 2 into 0.2, that is equal to 0.4 mm, that is equal to 4 into 10 raised to minus 4 meter. We know that magnetic force or ampere turns required F is equal to N into I, that is equal to H into L. Therefore, for air gap, F is equal to H into L, that is equal to 6.366 into 10 raised to 5 into 4 into 10 raised to minus 4, that is equal to 255. For the cast steel path, H is equal to B by mu 0 mu r, that is equal to B is 0.8 divided by mu 0 4 pi into 10 raised to minus 7 into mu r is given as 800. This is equal to 796 ampere turns per meter. Length of that cast steel path is L is equal to pi d divided by 2, that is equal to pi into total diameter 21 divided by 2, that is equal to 33 centimeter, which is 0.33 meter. Therefore, for cast steel path, the MMF or ampere turns required F is equal to H into L, that is equal to, here H is 796 and L is 0.33. This is equal to 796 into 0.33, that is equal to 263. Similarly, for cast iron path, H is equal to the same formula, B by mu 0 mu r, that is equal to B is 0.8 divided by 4 pi into 10 raised to minus 7, that is permeability of air, into relative permeability of cast iron, which is given as 166. This gives 3835 ampere turns per meter. Length of cast iron path is also the same as cast steel, that is 0.33 meter, and H we found as 3835. Therefore, magnetic force or ampere turns required F is equal to H into L, that is 3835 into length 0.33, which gives 1265. So for air gap, we found that ampere turns required is 255, and for cast steel path, the ampere turns required is 263, and for cast iron path, ampere turns required is 1265. Therefore, the total ampere turns required will be the sum of that of air gap, cast steel path and cast iron path. Therefore, total ampere turns required F is equal to ampere turns for air gap 255 plus ampere turns for cast steel path 263 plus ampere turns for cast iron path 1265. This is equal to 1783. In example 2, a rectangular iron core having a mean length of 100 cm is shown. The cross-sectional area of the iron core is 4 cm square. In the core, an air gap of 5 mm is cut. The relative permeability of this iron core is given as 1400. There are 3 coils A, B and C which are having number of turns 335, 600 and 600. Current flowing are 1.6 ampere in coil A, 4 ampere in coil B and 3 ampere in coil C. But we can see that in coil A and B the currents are in same direction, while in coil C the current is in the opposite direction. We have studied in Maxwell's right hand thumb rule, the direction of the flux depends upon the direction of current. If it is upwards, it is clockwise, and if it is downwards, it is anti-clockwise. Similarly, here coils A and B makes the flux flow in clockwise direction, while coil C makes it in anti-clockwise direction. The result is that the total flux will be the sum of flux developed by these two coils minus the flux developed by this coil. Therefore, total MMF F is equal to NA into IA plus NB into IB minus NC into IC. That is equal to 335 into current through that coil 1.6 ampere plus 600 into current through the coil 4 ampere minus 600 into current through that coil 3 ampere. Simplifying, we will get 1136 ampere turns. We know that reluctance depends upon the length and area of cross section. That is, reluctance S is equal to L by mu into A, which is equal to L by mu 0 mu r into A. Mu 0 is the permeability of air or vacuum, and mu r is the relative permeability of that material. Reluctance of this air gap SA is equal to this length 5 mm divided by mu 0, permeability of free space, into this area of cross section. That is given as 4 cm square. That is, reluctance of air gap SA is equal to L by mu 0 into A. That is equal to L is 5 mm. That is 5 into 10 raised to minus 3 divided by mu 0, that is 4 pi into 10 raised to minus 7 into area of cross section, that is 4 into 10 raised to minus 4. Simplifying this one, we will get 9.946 into 10 raised to 6 ampere turns per Weber. The mean length is given as 100 cm. Therefore, length of this iron path will be 100 minus this 5 mm. So, reluctance of iron path SB is equal to L by mu 0 mu r into A. Here L is total 100 cm minus this 5 mm. That is 100 minus 0.5 into 10 raised to minus 2 divided by mu 0 is 4 pi into 10 raised to minus 7 into mu r of iron path is 1400. 1400 into area of cross section 4 into 10 raised to minus 4. This is equal to 1.414 into 10 raised to 6 ampere turns per Weber. So, we got that reluctance of 5 mm air gap is 9.46 into 10 raised to 6, and the reluctance of that core is 1.414 into 10 raised to 6. Therefore, total reluctance is the sum of these two. Total reluctance S is equal to 9.946 into 10 raised to 6 plus 1.414 into 10 raised to 6. That is equal to 11.36 into 10 raised to 6 ampere turns per Weber. We know that in an electric circuit I is equal to E by R. Similarly, in magnetic circuit phi is equal to F by S. Therefore, flux developed phi is equal to MMF F divided by Yes, that is MMF is 1136 ampere turns and flux is 11.36 into 10 raised to 6. So this is equal to 1136 divided by 11.36 into 10 raised to 6, which gives 100 into 10 raised to minus 6 Weber. In this question, a steel ring of 20 cm diameter and a circular cross section which is having a diameter of 2.5 cm and having an air gap of 1 mm is given. In this ring, it is uniformly wound with 500 turns of copper wire which carries a current of 3 ampere. We are asked to calculate A. the magnetic motive force, then B. magnetic flux, C. flux density, and D. reluctance. Out of the total magnetic motive force developed here, we have to assume that 30% of the total magnetic motive force is taken by the steel ring. We can neglect magnetic leakage and fringing. To understand the circuit, it is easier to draw the electric equivalent circuit. This but EMF in this electric circuit is equivalent to this MMF produced or ampere turns F, and the flux passing is equivalent to current I. These two series resistances, that is RS and RA, equivalent to the reluctances of the magnetic circuit SS and SA. The mean diameter of the ring D is equal to 20 centimeter, that is 0.2 meter. Length of this air gap LA is equal to 1 mm, that is 0.001 meter, and the radius of the core R is equal to 2.5 divided by 2 centimeter, which is 1.25 into 10 raised to minus 2 meter. Therefore, the cross-sectional area of the magnetic core is equal to A, which is equal to pi into R square, that is pi into 1.25 into 10 raised to minus 2 the whole square, that is 4.91 into 10 raised to minus 4 meter square. First of all, we are asked to find the magnetic motive force. Magnetic motive force MMF is equal to F, which is equal to N into I, that is 500 into 3, which is equal to 1500 ampere turns. See, this is the total ampere turns. Therefore, magnetic motive force of steel ring is, in the question it is given that we have to assume that the steel ring takes 30% of total magnetic motive force. Therefore, magnetic motive force of steel ring is Fs is equal to 1500 into 30%, that is 30 by 100, which is equal to 450 ampere turns. So, magnetic motive force of air gap is Fa is equal to 1500 into balance 70%, that is 70 by 100, which gives 1050 ampere turns. Next, we have to calculate the magnetic flux. For calculating magnetic flux, first we will calculate the reluctance of air gap. Reluctance of air gap SA is equal to LA divided by mu 0 into A, which is equal to length of air gap is 0.001 divided by 4 pi into 10 raised to minus 7 into area of cross section is 4.91 into 10 raised to minus 4. 4.91 into 10 raised to minus 4, which gives 1.62 into 10 raised to 6 ampere turns per Weber. We know that in an electric circuit I is equal to E by R. Similarly, in magnetic circuit, flux phi is equal to F by S. Thus, for air gap, flux phi A is equal to FA divided by SA, that is equal to FA is 1050 divided by the SA we found out 1.62 into 10 raised to 6. 1.62 into 10 raised to 6. This is equal to 6.48 into 10 raised to minus 4. Next we are asked to find the flux density. Flux density is nothing but flux divided by area of cross section. That is, flux density B is equal to phi by A, that is equal to 6.48 into 10 raised to minus 4 divided by area of cross section is 4.91 into 10 raised to minus 4 meter square. 4.91 into 10 raised to minus 4. This gives 1.32 Weber per meter square. Next we are asked to find the reluctance. We know that in the case of electric circuit, resistance R is equal to E by I. Similarly, in the case of magnetic circuit, reluctance S is equal to F by phi. Therefore, reluctance of steel ring SS is equal to Fs divided by phi, that is equal to Fs we found as 450 ampere turns. That is equal to 450 divided by phi, which is 6.48 into 10 raised to minus 4. 6.48 into 10 raised to minus 4, which gives 0.69 into 10 raised to 6 ampere turns per Weber. We will be studying about parallel magnetic circuits in the next class. Hope this class also might have been useful to you. If so, please like it, share it and subscribe it by pressing that bell button so that you will be getting all the notifications of my future videos also. See you next time. Bye.